I'm Harley Kirchhoff, and this is my screencast on neuronal signaling and synaptic transmission. So for some background information, before I get into the details of neuronal signaling and synaptic transmission, I'm going to give some background information on what a synapse is. So a synapse is a specialized structure where two neurons come into close contact so that chemical or electrical signals can be passed from one cell to the next. Synaptic transmission happens from the axon terminal of one neuron to the dendrite of a neighboring neuron. In regards to information flow, neurons are referred to as either presynaptic or postsynaptic in relation to any particular synapse, with neurons being presynaptic when their axon makes a connection onto other neurons, and postsynaptic when other neurons make a connection onto their dendrites. So now we're into the beginning stages of neuronal signaling. So neurons need energy to generate signals. This energy is in the form of an electrical potential across the neuronal membrane. This potential is defined as the difference in the voltage inside the neuron versus outside the neuron. These voltages depend on the concentrations of potassium, sodium, and chloride ions, along with charged protein molecules both inside and outside of the cell. In the resting state, the voltage difference across the membrane is typically negative 70 millivolts, which is also referred to as the resting membrane potential. So the neuronal membrane that I'm talking about is composed mostly of a lipid membrane that blocks the flow of water-soluble substance between the inside and the outside of the neuron. It maintains separation of intracellular and extracellular ions and electrical charge that permits neuronal communication. However, ion channels and ion pumps serve as passages for ions to move across this membrane, making it semipermeable. Ion channels are proteins with a pore through their centers, allowing certain ions to flow down their concentration gradients. Voltage-gated ion channels are capable of changing their permeability of the membranes. They open and close based on changes in nearby transmembrane voltage. The voltage-gated sodium channel opens when the membrane potential is at negative 50 millivolts, allowing sodium ions to enter the axon. The voltage-gated potassium channel opens when the membrane potential is at 40 millivolts, allowing potassium ions to exit the axon. The sodium-potassium pump pumps sodium ions out and potassium ions in on a 3:2 ratio. This means that for every 3 sodium ions that are pumped out, 2 potassium ions are pumped in. And this creates a concentration gradient that creates forces of the unequal distribution of ions. The membrane is more permeable to potassium than to sodium, so some of the potassium is pushed out of the cell, leaving the inside of the neuron slightly more negative than the outside. Negative charge builds up along the inside of the membrane, while positively charged potassium ions are drawn electrically back into the neuron, causing the gradients of electrical and ion concentration to go in opposition to each other. This produces the resting membrane potential of negative 70 millivolts. This is the basis of the neuronal energy source. The signaling and transmission process begins when excitatory postsynaptic potentials, or EPSPs, at synapses on the neuron's dendrites cause ionic currents to flow in the volume of the cell body. The distance between neurons is too great for EPSPs to have any great effect because this is a passive current conduction and can only flow about 1 millimeter at a time. So now we're at the main part of neuronal signaling with action potentials. So neurons, instead of EPSPs, utilize the mechanism of action potential for signaling. An action potential is a rapid depolarization and repolarization of a small region of the membrane caused by the opening and closing of ion channels. Voltage-gated ion channels charge the action potential in the spike triggering zone and axon hillock. The electrical currents generated following EPSPs on multiple dendrites combine and flow across the neuronal membrane in the spike triggering zone, depolarizing the membrane. If the depolarization is strong enough where the membrane moves from its resting potential of negative 70 millivolts to a less negative value of about negative 55 millivolts, an action potential is triggered. This depolarized membrane value is the threshold for initiating an action potential. When the threshold is reached, voltage-gated sodium channels are opened and sodium flows into the axon. This depolarizes the neuron further, opening more sodium channels and creating a self-reinforcing cycle that lasts about 1 millisecond. The voltage-gated potassium channels then open, letting potassium flow out of the neuron. This outward flow of positive ions begins to shift the neuron back to its resting potential. The opening of the potassium channel outlasts that of the sodium channels, meaning the membrane is temporarily hyperpolarized, so the membrane potential is even farther from the threshold than its resting potential would be. During this hyperpolarization state, the voltage-gated sodium channels cannot open. This is referred to as the refractory period. However, the passive current flows down the membrane enough to depolarize the axon further down, generating an action potential in the next portion of the membrane, continuing down towards the axon terminal. To efficiently get to the axon terminal and complete the neuronal signaling process, action potentials need the help of myelin sheaths. So action potentials in myelinated axons only need to occur at the nodes of Ranvier, where myelination is interrupted. Myelin is a thick lipid sheath that accelerates the flow of action potential and makes it possible for it to flow more efficiently through the axon. Because action potentials only need to occur at the nodes of Ranvier, it creates the appearance that the action potential is jumping down the axon at great speed from one node to the next. This is referred to as saltatory conduction. So that concludes the neuronal signaling portion of the screencast, and now we're going to talk about the synaptic transmission portion. So synaptic transmission, the chemical portion of that depends on neurotransmitters. Neurotransmitters are molecules that are synthesized and stored in the presynaptic terminal before release. The postsynaptic neuron contains receptors specific for the neurotransmitter. When artificially applied to a postsynaptic cell, the neurotransmitter elicits the same response that stimulating the presynaptic neuron would. Categories of neurotransmitters include amino acids, biogenic amines, neuropeptides, and others that make up their own biochemical classes. So the chemical transmission process consists of neurons sending a signal to the cell across the synapse by releasing neurotransmitters into the synaptic cleft. When the action potential reaches the axon terminal, the terminal membrane is depolarized, calcium channels open, triggering small vesicles containing neurotransmitter to fire with the membrane at the synapse and release the transmitter into the synaptic cleft. The transmitter diffuses across the cleft and binds with specific receptors embedded in the postsynaptic membrane. This binding induces a change in the receptor, which opens specific ion channels and results in an influx of ions, leading to either depolarization, excitation, or hyperpolarization, inhibition, of the postsynaptic cell. Hyperpolarization of the postsynaptic neuron produces an inhibitory postsynaptic potential, or an IPSP. So after creating a reaction in the postsynaptic neuron, neurotransmitters must be removed from the synapse. Neurotransmitters can be removed from the synapse by active reuptake of the substance back into the presynaptic terminal, by enzymatic breakdown of the transmitter in the synaptic cleft, or by diffusion of the neurotransmitter away from the region of the synapse or site of action. Neurons can also communicate through electrical transmission in electric synapses. So in this form of transmission, neuronal membranes are touching at specializations called gap junctions, and the cytoplasms of the two neurons are basically continuous. These channels create pores connecting the cytoplasms of the two neurons. The two neurons are now isopotential, meaning that electrical changes in one are reflected instantaneously in the other. This is especially useful when information must be conducted rapidly. It's different from chemical transmission because it doesn't utilize neurotransmitters or synaptic clefts. So to sort of explain how all of this can apply to a real-world situation, I'm going to talk a little bit about Novocaine. So Novocaine prevents neurons from communicating by blocking ion gates, therefore preventing the action potential that releases the information transmission of the neurotransmitters from neuron to neuron. This prevents us from feeling pain. Thank you so much for listening.